let's talk about the four subspaces. So I have a matrix A that I'm going to take to be m by n, and I need to know where that thing maps to and from. So what's the domain of my matrix A if it's m by n? It's one of these big old puppies. Which one is it? Is this n space or m space?
M.
I think I heard you say n.
I said M.
Damn it, Cody! Take
As
a
in-
hint. All right, so let's work our way through it. So if we're going to take a matrix A m by n, and we're going to multiply by a vector, right? So I'm thinking I'm going to multiply by a vector here. That vector is a set of entries in a column. So that vector is something by 1. So in order for me to make this multiplication work, I need this number here, n, to match this number here. So my multiplying vector has to be an n-dimensional vector. And then it's going to end up in Rm. And this, I guarantee you, is the number one thing that you'll leave this course confused by. You will forever be flip-flopping these things because I am forever flip-flopping these things. Whenever I'm unsure, I just write it down this way with this little matrix times a vector and check those inner numbers. That's ultimately what you have to do. I also oftentimes look up that it's rows by columns. It really happens to me a lot. I know it's confusing because it's pretty arbitrary. So I've got my n space in my, what is this thing called? What is Rn here? Is that the range, the codomain, the domain, the null space, the column space? I've got a lot of freaking words now.
Is it the codomain?
Close. The codomain's this one over here.
So
What is domain, Alex?
My name is Joe.
Too soon.
Oh, it's so sad. I miss him so much. His really tremendous mustache. All right. At any rate, I've got a domain over here, right? I've got a codomain over here. And I need to remember that the codomain is just kind of the stuff you're aiming at. It's not necessarily the stuff you're hitting. Does that make sense? So I'm going to have a tendency to, instead of writing codomain over here, I'm going to write target. But codomain's also fine. All right. So then the question is, what are the other subspaces I know of so far? So far, I know of a column space of A, right? What is the column space of A? Where do I get that thing? So remember, this is the span of all of the column vectors. Now, remember, the column multiplication picture tells me that this thing, right, the span of all the columns, is also identically the range or the image of A. You guys with me on that?
Yeah.
So this thing is a subset of Rn. Is that right? Where does this one live? Does this live before the arrow or after the arrow?
Before?
I
So-
think it lives after.
Yeah, things in the domain live before the arrow, right? They're things that are going to get mapped. Things that live after the arrow are things that have been mapped. So when I take a vector and feed it into the matrix, I'm going to get an element of the column space. So that thing has been mapped. So these are in Rm, right? They're in the range, which is a subset of the target. You guys with me on that? Okay. Now, I have one more space that I know about already, which is the null space of A. What's the null space of A? It's the set of vectors such that what happens?
A maps to 0.
Perfect. A maps them to 0. So AX is the 0 vector. So where does this set live? Are these vectors vectors that get mapped or vectors that have been mapped? The X's.
Vectors that get mapped.
Good. These are vectors in the domain. So these are Rn. And then remember we have this counting theorem, right? What does the counting theorem say? You guys remember what the counting theorem says?
Isn't it just R plus N minus R equals N? Or is it the N minus R equals F?
Well, yeah, I mean it
N
boils
is-
down it boils down to R
N
plus
is equal to. Oops, sorry.
No, go for it.
N is equal to R plus nullity.
Yeah, so it does boil down to R plus N minus R is N, but that's a little bit much in terms of like because that's true of numbers, right?
Yeah.
So this is special in that this is the rank of A plus the nullity, which is really the dimension of the null space of A, is equal to the dimension of the domain. So I'm going to leave that as lowercase m. Oops. I promise I know what I'm doing here. I don't actually have any idea what I'm doing with this. Okay, so that's the counting theorem, right? Okay, so quick question. I have thought this through for my matrix A, right? What if I thought this through for my matrix A transpose? How big is A transpose?
N by M.
Perfect. It's n by m. And this thing maps Rm to Rn. You guys see that? Okay. Now, here's the thing. All this stuff I just wrote down for A is also kind of true for A transpose, right? I'm going to need to do a little finagling about exactly where things live, So let me think that through. So the column space of A transpose, and I'm really aggressively going to leave myself a little space over here to the left, right? So make sure you leave some space there because we're going to fill in what this thing's real name is in just a hot second. Okay, so I've got the column space of A transpose. That's going to be the span of all the columns of A transpose. And this is going to be equal to what of A transpose? And it's going to be a subset of something. So fill those blanks in for me. What was the column space for the matrix A earlier? Like up here? Column space for matrix A was the range of A, right? So what's the column space of the matrix A transpose?
The range of A transpose?
Yeah, shit, it's still the range. Nice. And that now is a subset of which space? Where does that thing live?
Rn?
Perfect. That lives in Rn. Okay, now let me think here. Okay, so the column space of A transpose. Let's see. Well, I guess I talked about the column space of A transpose. Maybe I should talk about the null space of A transpose. So that's going to be the vectors x with, oh, I'm calling them vectors x. I probably shouldn't call them vectors x. I'm going to call this a vector y, just to be really suggestive that it's in the kind of codomain space for A, right? So if A takes x's to y's, then these are kind of the y's. You guys all with me on that? That's maybe a little weird. I'm looking up here and I'm thinking, okay, so A is the function I'm really interested in. So the domain of A, I'm thinking x's, and the target, I'm thinking y's. That's just thought. It doesn't have any meaning at all, right? So here, when I'm talking about y's, where do the y's go if they're in the null space of A transpose? Like, tell me about that definition. Feel free to use the definition of the null space of A.
A transpose Y is the zero vector.
Perfect. Good. Okay. Kick ass. Now, well, now I'm interested in relabeling my column space of A transpose. So let's get a real name down for that thing. How does that relate to the matrix A? What are the columns of A transpose here? And I said this is the span of the columns of A transpose.
It's the rows of A. Kind of.
Not even kind of, exactly. Yeah, that's perfect. So if the column space of A transpose is also the span of the rows of A, don't get creative here. What would you call that?
The row space of A.
Perfect. Okay, and this is going to start to tie things together a little bit. This null space of A transpose, that's a little weird. We're going to end up calling this the left null space. I'm going to tend to refer to that as the null space of A transpose. But the book's going to call it the left null space. I don't really like thinking about left multiplication, so I tend to avoid it when I can. But really what they're getting at is that Y transpose A is also going to be 0. They're just saying, like, okay, look, if you multiply from the other side, you get 0. Does that kind of make sense? Don't sweat that much. It's not very important. What is important is that you know it's the null space for the transpose matrix. And now there's some kind of picture thing I need to draw here. So let me see if I can find this thing. Oh no! Oh, epic fail, Joe. Epic fail. I don't have this prepped. Where is it? If only we had the picture somewhere. This picture.
That was going to be one of my questions, if we could go over that picture.
Yeah, absolutely. Let's pull that thing in here. How do we insert things? I should have just had this on a clipboard, but I was too stupid to have done it. Where did that go now? Downloads. Strand cover. Insert. Okay. So, I have one more counting picture or counting theorem thing I want to talk about, but I want to get some labels on this picture right here, right now. All right. So, let's think about boxes and where they live. All right. Where does the column space live? Right-hand side of picture or left-hand side? Remember, the matrix A is going this way. So this is R. Which one is this over here?
And
Good. That's Rn over there. Here's Rm over here. Let's see. So it's telling me that AZ is going to 0, right? You guys see that line right there? So if AZ goes to 0, where does that mean Z lives?
In the null space.
Perfect. Oh, that's not going to work at all, Joe. So this green box is the null space of A. Couple things. One, why is it flat? You guys see that thing looks flat? It looks like a chunk of a plane, right? It's meant to represent a whole plane, but there are some limitations with drawing n-dimensional space broken into 2 pieces and put on a piece of paper.
I was going to say it's probably just because it's on a flat piece of paper.
Yeah, one of the reasons okay, so if I had to draw this picture and I didn't intend it to be flat, I would be doing something like this, right? I'd be like drawing a blob and then separating it into 2 pieces. That's what naturally I would do as a mathematician. So maybe that is like too much. Like I'm leaning into this a little bit much, and that you should know that, and that's probably not true. That's probably an unreasonable assumption. But there is a good reason that that thing is drawn as something flat instead of something wobbly like this. Why? Why would I think flat instead of wobbly? The null space is 2 things. I'm going to keep saying this over and over until it sticks. You should just get this tattooed on your forearms. The null space is 2 things. It is null, and it is also
A space.
a space. Spaces are flat because they contain all the linear combinations. They have no choice but to be flat because they are all the things. You guys see that?
I'm going to have to say no.
Okay. What is the span of 1 vector?
A line.
What is the span of 2 vectors?
A plane.
Good. Now scale up. Things are flat. That's not really, I know that's not really fair.
I was gonna say, like space, like come on, like R3.
Yeah, R3 as a subset of R4 is flat, right? The span of 3 vectors in R4 is it's all perpendicular to one particular vector, right? You can still pick a normal vector out of everything else.
Okay.
We're going to do a little bit of that going forward. Like there's a really good reason that there's a right angle here. And we're going to get to that in a chapter or two. But for right now, I want you to recognize that the green thing is the null space, and it's flat because it's a space. Let's see. So let's look at AY is B and AX is B. What do those mean? Those mean that when I take A and apply, or sorry, when I take Y and apply A to it, I get B. See this vector B? Where does that vector B live?
In the in the column space.
Perfect. So the red thing over here is the column space of A. See that it lives in Rm? If we scroll up, we remember that the column space lives in Rm. You guys with me on that? All right, now this is the part where we stitch in these weird ones. So there's this yellow box, right? You guys see the yellow box there? Quick question. How big is the yellow box?
About as big as the red one.
Same size as the red one. What was the red one? The red one was the column space of A, right? So the size of the red one, this size here, the dimension of the column space of A, is the rank of A, right? You guys with me on that? The rank of A is the number of linearly independent columns, right? Which is also the number of linear independent. This is so freaking cool. You guys are not. I can't tell whether it's just that your mic's off or that you're not as enthusiastic about this as I am. I just love this part of linear algebra. This is the number of linearly independent rows. They're the same thing.
Nice.
They're the same number. They're the number of pivots that the matrix has. So the fact that the red box over here has a size, this yellow box, that's the row space.
Now, I can't help but notice that the green and blue look the same size too, but I know that the null spaces don't have to be the same size.
I know, and I'll never forgive Strang for not just making them a little bit differently sized on the cover. I just never will. I should just Photoshop this cover the way I want it to be. I really wish that he had just made this, like, all he had to do, you know? Like, just one friggin' thing was just make this one just a tiny bit bigger. It doesn't even need to be much. It just needs to be slightly different. So this is actually a really good point to wrap around and see if we understand. So what is the blue box? Like, I think we're kind of guessing at what the blue box is. Anybody want to articulate that for me? So far, I've got the null space for the matrix. I've got the column space for the matrix. I've got the row space for the matrix, which is the column space for the transpose. So what's the other box I have labeled? What's the other space I kind of named here?
The null of A transpose?
Yeah, so there's kind of one thing left. There's 4 boxes. Maybe the process of elimination would tell you that this probably ought to be the null space of A transpose. That's true, and the reason that Jacob and I are having this little, like, we really wish that Strang had put just a little bit more blue on the box here. Why are we having that? Like, why is that a thought? So, to reiterate, this was the dimension of the row space was also the rank of A, right? The counting theorem would tell you that how big is this null space? What's the dimension of the null space of A? What'd the counting theorem say? I'm so excited I could just dance anyways. What do you got? Come on. Lame. Go ahead, Jacob. Hit me.
Okay. It's the rank, or yeah, no, it's the rank. Why am I drawing a blank all of a sudden? Holy crap.
Nullity.
Yeah, nullity. Oh my god, sorry. I'm
No worries.
doing
It's
my
okay.
homework right now, and my head is in a completely different space.
Okay, so the counting theorem says that rank plus nullity is the dimension of the domain.
That's right.
Right. So in this case, that means that I can say the dimension of the null space is the dimension of the domain minus the rank of A. Now, the thing is over here, I should be able to say a very similar thing. So if I consider the transpose matrix, I'm looking for the dimension of the null space of a transpose, right? And I'm pretty sure that the counting theorem applies to A transpose too, right? Like, I proved that thing for a general matrix. Didn't have to be A or A transpose. It was just some matrix. A transpose is some matrix. So this should be the dimension of the domain minus the rank of the matrix. Now, the thing I know now is that when I'm talking about the rank of a transpose matrix, that's the same as the rank of the matrix itself. So this should equal M minus the rank of A. Oh yeah, so the counting theorem is, I'm just answering a question out of chat for people watching a video. The counting theorem is that the rank of A plus the dimension of the null space is the dimension of the domain space. Right? So applied to A transpose, that tells me that I have M minus the rank of A. And this is the thing that Jacob and I were whining about, that these two things don't have to be the same. And this is the thing that I will never forgive Strang for, in spite of writing what is otherwise, I think, one of the better books on the topic. I really just a little sliver of blue, man. Come on.
So, like I was saying, I was just doing a problem, and it involves drawing a picture like this.
Mm-hmm.
So if the column space or row space was equal in dimension to its null space, would that mean those squares should be the same size?
So the column space and the row space always have to be the same size. Right? They can't actually be different size.
Oh, yeah.
Now, the thing is, in this picture, one of them is kind of tipped.
Mm-hmm.
You guys all see that? And that's possible. So just because they're the same size doesn't mean they have to be the same thing.
Okay.
Does that make sense? I hope that distinction makes sense. Like the x-axis and the y-axis have the same dimension, right? They're each dimension 1 as subspaces of R, whatever. But they're not the same space, right? Even though they're the same size, they're different spaces. So same thing here, right? The column space and the row space can be wildly different spaces, but they have to have the same dimension. Everybody good with that?
Yep.
So,
Okay. Now, there's some more stuff we're going to come back to in this picture. We're going to kind of keep touching on this picture for the next couple of days. And in fact, we'll touch on this. We're going to keep coming back to this picture occasionally throughout the course. There's a couple more things I want to touch on just before we leave this picture the first time. One of those things is I want to talk about this funny little arrow out here. And can we maybe explain what the hell is going on with the x equals yz arrow here?
so I was actually going to ask about that. I was thinking it was like the function form of the matrix, almost like when we were first learning, we had like the plane and then we turned it into a matrix.
Okay, yeah. So here's maybe let me highlight a couple things. Y is this arrow here, right? You guys see that? So Y is in the row space. You guys hear me?
Yeah.
Where does Z live? So Z is this arrow here.
Null space.
So Z's in the null space of it. Now, this isn't yet clear. I have a little work to do with this. But X in the domain, so X in Rn, can always be rewritten as a Y in the row space plus a Z in the null space.
Oh, yeah, that's what we were doing in, what was it, 3.4 or something?
Yeah, this is exactly the same, like, composition into the complete solution, right?
Yeah.
I'm thinking about it. It's a thing in the space that goes somewhere, right? Plus something that gets mapped to 0. So when I'm solving equations, right, really we're kind of reaching for the solution to ax equals b, or right, ax equals b here. So when I'm thinking, all right, so what's ax? Well, ax is a done to y plus a done to z. Well, a done to z gives you 0. And if ay is b and x is y plus something in the null, then x goes to the same place that y does. Does that thought process sort of make sense? So this little set of arrows here is explaining the complete solution. Like, that's what all those little arrows are about. Now, I glossed one thing there. I said something, and I said it was a little bit of a lie, and that I hadn't explained it yet. What was the thing that I kind of leaned on to lie here? Just a tiny little trip. I said this kind of funny thing. I said any x in Rn can be written as x is y plus z with y in the row space and z in the null space. Now, that's not in evidence. I haven't demonstrated that that's true yet. You guys with me on that? So why would I think that's true? Other than this picture, right? Which could be a lot. Like, Strand could be, he could be lying about more than the size of the blue box. He may have it out for us. So let's put on our friggin' skeptical hats and see if we can believe or disbelieve Strang here. So, or me. Like, is this right? Why is there any reason at all that a vector could be decomposed into something in the row space plus something in the null space? Do those even make up the right size? Could that even be true? How big is this space I'm talking about? How many x's are there? What's the dimension of the space that x's are coming out of?
R, the rank.
Well, if they're coming out of the row space, I think they have the dimension of the row space is the rank, right?
Yeah.
I've got that written down right here. Right, so that's this part, the yellow part. That's good, I need that. How big is this whole thing on this left-hand side? How many dimensions does that space have, this whole thing?
N.
Perfect. That's n space, right? How big is the null space? What's the dimension of the null space?
N minus the rank.
Ah, cool. So at the very least, I can give you a size-wise, like size-wise, this makes sense, right? There's rank A things in the yellow. There's n minus rank A things in the green. Together, that makes n. Okay, this might be enough. What do I need to know? I need to know one thing to be sure that this is actually enough. I need to know they don't overlap at all. You guys see that? If they overlapped, right, if I was like, okay, so a plane and a line together make all of R3, right? You'd be like, yeah, bam, just like that. Planes with a line stuck in it. Of course, I can decompose any vector in R3 into some vector in the plane plus some vector in this line. Okay, see that? Like, that totally makes sense. But what if they don't meet that way? What if they're like this? What if it's a plane and a line in the plane? Well, then I can only get stuff in the plane, right? You guys see that?
Yeah.
Okay, so how do I know they don't overlap? I need an argument for why something in the null space can't be in the row space, or why something in the row space can't be in the null space. Okay, I've got a couple options here. I've got a import from future, like I can go out and get an argument that we're gonna deal with in a little bit that kind of explains that little right angle thing. Or I've got an argument that relies on something that we did a long time ago. Do you want the right angle argument right now, or do you want to go get the older thing? Your choice. You want to hear them both?
Yeah.
Okay. All right. So why can't a vector x be in both n of a and row of a? Okay. Let's do new things first, I guess. Okay, so let me look at my matrix A. And I'm kind of interested in the row space, right? So I'm going to put my rows in here. So I'm going to go, all right, here's my matrix A broken into rows. Shouldn't have gotten ambitious and put 3. Let's see. How many rows does A have?
N. M. Oh wait, it's M by N. So M.
Perfect. Good. So there's M rows, and then I'm multiplying by a vector X, right? So I've got a column vector X like this. You guys see that? Okay. Let me suppose that X is in the null space. You guys with me on that? All right, so if I'm supposing X is in the null space, then where does this go? What's the result of taking AX?
0.
Perfect. The null space is 2 things. It is null, and it is a space. All right, so it's all the stuff that goes to 0. So I know the inevitable result of this is 0. This 0 is since X is in the null space of A. Okay, what else is this? Like if I had to do that a different way, I'd like do some pixie flips here, right? Pick up and drop on, right?
X
How do I write
times
this down?
X times the rows of A.
Perfect. Yeah, it's also a column vector made out of R1 dotted with X and R2 dotted with X. And on here down to RM dotted with X. You guys see that? Okay, now if this is the 0 vector, so this is just the row multiplication picture, right? This isn't anything special. Well, okay, it's kind of friggin' special, but it's just the row multiplication picture. So if this is indeed the 0 vector, what do these 2 facts together mean? These mean head equals to explode. This should be like a head popping moment. What does it mean? So this would mean, right, that Ri dotted with X is 0 for all i's. What does it mean when the dot product's 0?
Oh,
Parallel?
Close.
perpendicular.
Perpendicular.
There's the brain pop.
Yep. So this means that X is perpendicular to each of the rows, right? But not like one of the rows. It's perpendicular to all of the rows. You guys see that? So if it's perpendicular to all of the rows, in the like Calc 3 style analogy, this thing's acting like the normal vector to the plane made out of the rows. Now that's a little bit of a lie here because there might be more rows than that, right? You guys with me on that? But this means that if X is in the null space, it's perpendicular to all the rows at the same time. You guys see that? So what this means is that if I had to define perpendicular to a space, this is how I would do it. Right? X is perpendicular to the whole row space. And remember, X was any vector in the null space. So the whole null space is perpendicular to the whole row space. You guys see what I mean by that? It's maybe not obvious that this can happen. Like, I believe it in R3, right? So in R3, options are either all the things and the zero vector, or two of the three dimensions and the third one as a line, right? So those can be perpendicular, I believe that. Zero is perpendicular to all of the things anyways, so that one's fine. And then the only other option is that, well, is the same thing but backwards again, right? So just on the other hands. The weird thing is that in R4 you can have two planes be mutually perpendicular, which is real hard to do with your hands. You guys see that? It's like they intersect at 0 at 90-degree angles. It's real hard to draw. I don't have a good picture for it. I think the best picture I could draw for it would be to do something like this. And then maybe I'd color this one red and this one green, or yellow and green, and it'd look a lot like Strang's picture, right? That's what he means here. So he's got two flat things that are perpendicular to one another. You guys with me on that? So that's like kind of borrowed from the future. Like, we're going to talk more about perpendicularity here going forward. But just like, that's the argument we're going to use later. So that would tell me that since they're perpendicular, they of course can't overlap at all, except for at the zero vector. You guys on board with that argument?
Yeah.
The other way we could see this is we could look at doing elimination. And this is what Strang's does. This is what Strang's argument consists of, which is part of the reason I feel okay kind of leaving it off. So if I think about having, say, my matrix A made out of R1, R2, Rm, right? So I've got my matrix A here. Dot, dot, dots in there. What happens when I apply an elimination matrix to this? Like, if I'm looking for pivots, right, I'm just going to keep eliminating. So if I do, say, like I think about like the EM1 elimination matrix, right, applied to this thing. What's that going to do? Like, if I'm thinking run the EM1 elimination matrix, I'm kind of targeting this first coordinate down here for elimination, right? What's the steps involved in that? Like, if you had to do elimination, so like, here's a little matrix. If you had to make the E21 matrix on this, what would it be?
Row 2 minus 3 row 1.
Perfect. Yeah. So you'd kind of go, all right, so we're going to do the new row 2 is going to be the old row 2 minus 3 row 1. Notice the new row 2 you made is a what of the old row 1 and row 2. What is this thing? You guys see that's a linear combination of row 1 and row 2. So where is it still? It's still in the row space. You guys see that? So because I did this, I made this linear combination. That new vector, this guy, That's still in the row space. I didn't change the row space when I did that elimination step. I changed the way it looks, but I didn't change the space. You guys see that? I think this argument is a little weaker, personally. Like I don't find this argument to be quite as convincing because I love that perpendicular piece so much that I just can't help it. But this argument also works, right? So because I'm taking a linear combination at every elimination step, the row space isn't getting smaller. The number of pivots isn't going down, so I'm not losing anything. And it's not changing because I know that each new row is still in the row space. You guys with me on that? So since the dimension's not going down, and because all the elements are still in the same space, I know that I still have the same space. The column space, on the other hand, so if you're doing elimination, the column space might change. You might get something different. So be careful. The elimination matrix doesn't have the same spaces that the original one did. It has similar, like the sizes are all still the same, right? When you do elimination, the rank doesn't go down, but the column space might rotate around on you. So you gotta be a little careful with that. The row space, however, does not. All right. Examples, I'm assuming, would be good. Let's have a quick. Where did the example go? Okay, so find all four subspaces for the matrix 1, 2, 2, 4, 4, 8. Oh, and I'm going to do this.